Okay, let us start, and let me first welcome those of you that I didn't see last week and wish also you a Happy New Year. And we did only cover a few topics last time, actually only one topic, and what we did, actually we proved that the KKT conditions, these first order necessary conditions that we know since Christmas, that they are also sufficient for global optimality when we have a convex problem. So that was the topic of last time, and today we want to continue with the optimality conditions for constraint optimization and conclude that chapter, and then we go into the algorithms to solve inequality constraint optimization problems. Let me first recall a concept that we already introduced, but I want to formalize a few things around that, and that is the topic of complementarity. So you remember an inequality constraint can be active, that means it's actually touched by the point, but then there are different degrees of activity and they depend on the Lagrange multipliers. So let me just continue with section 3.13.4 about complementarity. And complementarity refers to the last three of the conditions. You remember in these KKT conditions, there were some conditions on the gradient, on the equalities, but then there was hi of x star should be bigger than 0, mu I star should be bigger than 0, and the product of mu I star with hi at x star should be equal to 0, and this should happen for I from 1 to q, where q was the number of inequalities. And these are the complementarity conditions, and as I discussed already before, they describe a set in the space of hi x and mu I, which is only allowing hi to be positive, that means here, mu I to be positive, that means here, and the product of the two must be 0, and that actually restricts us to this part of the set. So it's an L-shaped set in which the function h and the multiplier can live in order to satisfy these optimality conditions, and and any point that satisfies these things is satisfying the complementarity conditions. Please note that due to the fact that we have a corner here, this is a non-smooth set, and this set is actually the main, this non-smoothness is the main reason why algorithms for equality constraint optimization are difficult. And now you can imagine, how do we call a constraint which is living here? If hi is positive, strictly positive, then the multiplier must be 0. That's what these KKT conditions imply. That basically means it doesn't contribute to the Lagrange gradient. That's, you remember, right? But how do we call such a point? We call this inactive. Yeah, so the constraint is inactive. That's what we already defined. Yeah, so that means I is not element in the active set. Right? So that is what this point here would mean. When we are here, when the constraint is 0, then here we would be active. And we would actually say that I is element in the active set at x for any point where the h is 0, including the 0. But now there's this interesting point, 0 where both things are 0, and we want to give a special name to this, and actually we give a name to this, we call it weakly active, because the multiplier is 0, and here we call it, if it's excluding 0, we call it strictly active. So we introduce new sets. So it's a definition now. Given a KKT triple, x star, lambda star, and mu star. And when I say a KKT triple, then I mean LICQ and KKT conditions are satisfied. Yeah? LICQ and KKT at this point. Yeah? So that's one of these points that satisfies the necessary optimality conditions. We define the active set. Of course, we know that already. That was the set A of X star is the set of all indices, so that HI at X star is equal to 0. So that was the active set. We know that already. But we also define the weakly active set. And we call it alpha A0. And it depends not only on X star, but it also depends on the multiplier values. So that's why we need the KKT triple to define it. And it basically depends also on the mu's, actually the inequality multipliers. And it's all the i's which are in the active set, which also satisfy that the mu I is equal to 0. So these are those indices. And then we can also define, on the other hand, the strictly active set. Which we denote by alpha plus, and it depends on X star and mu star. And it's of course given by the other indices in the active set at X star, which satisfy that the multiplier is strictly positive. Mu I star is bigger than 0. Okay, so we call a constraint weakly active if it's active and the multiplier is 0, and we call it strictly active if the multiplier is strictly positive. We need that because, some algorithms are having difficulty with weakly active constraints, so they create a special difficulty. But also for the optimality conditions already, this difference needs to be made. So, in particular, for second order conditions, we really need to make a distinction between the two, and that's what we will do in the next section. So, maybe I should first note that alpha or A of X star is of course given by A0 X star mu star unified with A plus X star mu star, and they are also disjoint. So their intersection is 0 and their unification is the active set. That's clear, right? So we will now look at the second order conditions for optimality. And if there's no question about complementarity, I would leave it like this at the moment, and we go on with second order conditions. Okay? And everything was so simple when we had equalities, and things get more complicated now. So there's a set that we need to define and which makes use of these strictly and weakly active constraints. And maybe I give you some intuition at the beginning. When we have, and this is just by a drawing, not with numbers. So if you have a constraint optimization problem, for example, with a two-dimensional space and two constraints, two inequalities like this, and an objective that goes down here. So the gradient of the objective would be here. Then this is a minimizer, and you see obviously this is a unique minimizer. In this case it's even convex, so this would be a nice optimum. So now the question is, what is the tangent cone here? Now the tangent cone is, of course, all directions in which we can move here. And if you think of equality constraint optimization, there we said, okay, the Hessian needs to be positive definite in all directions in which you can move, basically in the directions of the tangent cone. That was for equality constraint optimization. But if you look at all these directions, you see that even up to first order, you go up. You go uphill in all of these directions with respect to that objective. Yeah? So this objective increases here, and every vector in the tangent cone will increase. So there is no need actually in this case to even check second order conditions, because it's, you cannot move in any direction where the first order, the gradient is already telling you you will get worse. So actually the second order terms are not necessary in this example. Yeah? So we cannot just say, require, like we did for equality constraint optimization, that some metrics must be positive definite on the tangent cone. Tangent cone is not the right concept. Maybe I give another example, so that we get already a bit of an idea. Let me just, I will just draw a circle. Inside is feasible. I will make some level lines, so like in this example. But these level lines are so that I get more slope when I'm approaching. So basically I get steeper and steeper here. Yeah, so it's really going down. So if I would draw a line from here and then plot this from the side, then my objective function would go boom, down until it hits the boundary of the circle. So that's like a side view of the same objective. So you would have negative curvature in this direction, and then you hit the optimal point, which is here. So the optimum is, of course, a nice and well-determined thing. If you plot it from the side, this is the objective in one dimension, and here you see it from the top with 2 dimensions. You would see, okay, what probably you can move in this direction or in this direction, and then the first order information will not tell you anything. But if you would move in this direction for the same argument that we had here, which is a feasible direction, so it's part of the tangent cone, in this direction you don't have to check second order information, because when I move in this direction I directly go uphill with my objective. So my first order information already tells me that I'm at a minimum. So I don't need to check positive definiteness of my second order information in this direction. So we need to exclude some directions from the tangent cone before we can even require some second order conditions. And these conditions we now need to define, and they are called the critical cone. So let me define the set, which is basically in this example corresponding to the directions which are here, the flat direction, so to say, where I don't see from this plot directly that the objective increases linearly. I see maybe that there's positive curvature, but I don't see that things up to first order increase already. Here actually the critical cone would be just the point 0. They cannot move in any direction without directly having first order increase in my objective. So the critical cone, let me define it. It's a subset, and so let me define it. So we regard a KKT point x star, lambda star, mu star, including LICQ. So then we already know linearized feasible cone and tangent cone are the same, right? But the critical cone we call it curly C. It depends on x star and also on mu star, like the active set. It's the set of all directions P which are in the tangent cone. Sorry, I wrote the tangent cone like this, I think, right? And omega is the feasible set. So it's directions in the tangent cone which have the property that maybe I first define it, that they are not changing the strictly active constraints. So that means that the gradient of hi x star transpose P should be equal to 0 for all I element in the strictly active constraints. So it's a subset of the tangent cone. And we could alternatively write it also this way. So it could be also just all directions in Rn, which satisfy all the conditions that things satisfy in the tangent cone, which are the same as the linearized feasible cone. So it's actually nabla G x star transpose P equal to 0. That's a vector valued equation, right? So they should be 0. And then for all H nabla H I x star times P should be bigger than 0 for I element in the weakly active set. So that was for all inequalities that are weakly active. It's the same thing that we had for the tangent cone, but then this additional condition that we have nabla H, maybe I give it a different index just for fun, is strictly equal to 0 for J element in the strictly active set. So we get this extra restriction here of the tangent cone. It's a subset, which is, if this would be an inequality, it would be exactly the tangent cone. But we make this inequality for the strictly active constraints an equality here. And then we have just prove this. Do you agree that we should prove that? It's relatively straightforward with the tools that we have already on the blackboard, so it's good to do that before the break. We do a sketch of the proof. And we do it for both theorems together. And we go the same trick as before. You remember the tricks that we did before was actually that we say on some certain set, the objective and the Lagrangian are the same. And the set that we choose here is actually this set. And then on this set, we use the equality of these two things, and we show that second order information leads us to either something that is so that we have either semi-definiteness or positive definiteness, and then we draw our conclusions from it. So let me just start with this set, regard omega bar of x star and mu star, from this equation, which is a restriction of the feasible set. Yeah, so that is actually this set that I illustrated here for that example. And then on this, we regard the Lagrangian only on this set. So let us just write down the Lagrangian as a function of x, and I will just write it down, and then we can argue that it's the same on the set. So we have f of x minus, how do I do it? I do it this way, lambda I gi of x, and here I take the optimal multipliers, so the ones with a star. I will also add over all my equalities, and I think I will only add over the active and the inactive constraints, right? So because there are some multipliers which are anyway 0, the ones for the non-active constraints, but I will not even regard them in the sum. So here I have I in the, let's do it in the same order, in the weakly active constraint, and allow me that I omit the index of the set. So the set, of course, also depends on x star and mu star, but this is now mu I star times h I x, and here I have the sum over all the other indices which are in the strictly active constraint set, mu I star times h I x star. And I regard this now on the set for all x element in this restricted feasible set omega bar, we actually have that these things are equal to the objective. So what we have is that this is equal to 0. This thing is, anyway, I mean, these multipliers are 0. So I could have dropped that already from the beginning, right? Here the multipliers are positive, but I make this thing because it is inside this omega bar set where I restrict actually the strictly active inequalities to be equal. So on this set I really have we have Lx lambda star mu star is equal to f of x. So on this set I can actually regard my Lagrangian as the objective. That's a very nice thing. Like before in the equality constraint case. And then the obvious thing that I can now do is I can use the fact that if I Taylor expand this thing, my first order term, namely the Lagrangian, drops because I have the stationarity. So now I can actually do a second order Taylor expansion, and let me just do it with second order terms. So I can say f of x is equal to L of x lambda star mu star, which is given by I make a Taylor at x star for x element in omega bar. So I will only regard these points in this critical restriction of the feasible set. And then I have here the objective value, of course, f of x star. So that's the objective value here, plus a first order term. Then I take the Lagrange gradient at x star, lambda star, mu star, transpose times x minus x star. So that's the first order term. I also add the second order term. So here I have x minus x star transpose with a 1/2. The second order expansion of the Lagrangian at x star, lambda star, mu star, x minus x star, plus some terms which are of higher order, so it's small o x minus x star. And now we are actually already finished, nearly finished. You see that this thing is 0. So we see that this is the objective, this is a quadratic term, and this quadratic term can either, I mean, it will, for small enough x minus x star, it will always dominate that term, as long as it is non-zero. So what we get here is, again, if we move in a direction which is, so if this is positive definite, like in this second order sufficient conditions, the second theorem, this is a positive definite matrix in all directions which are in this feasible cone, in this critical cone, yeah, then this term, because it's positive definite, will always dominate that term, and we are definitely at a minimum. If, on the other hand, there is, if this is a if it is a minimal point, and this matrix would not be positive semi-definite on this space, then there would be one direction in the critical cone where this would have a negative eigenvalue, and if that would have a negative eigenvalue, this would already mean that you go down when you are moving in a feasible direction on the set omega bar. So, by the same argument as before, we see that we have to look at the second derivative of the Lagrangian. And the reason, of course, was that we can use stationarity and the fact that the first order derivative of the Lagrangian vanishes. So that's a sketch of a proof. Gives the intuition. It's not absolutely formally watertight, I would say, but I think at least I get the intuition behind it. what I wanted to do now is illustrate that with one example which is a bit less, a bit more interesting in the sense that we have a weakly active constraint. And let me just invent one example. So what would be so it would be actually minimizing x squared subject to x bigger than 0. I mean, it's not an extremely exciting example, but it is some example I want to just use for illustration. So if I visualize that from the side, here is x, here is f of x, right? So what is my active set? I mean, there's only one constraint, so the active set is the same as the weakly, maybe I should say, active set is just the constraint which has the index of 1, because I have only one inequality anyway, and I would say h1 of x is equal to x, right? So this function is h1. But if I look at a KKT point, I can actually compute a point, and actually x star equals 0 and nu 1 star equals 0 is a KKT point. You can easily show that. I mean, the gradient of that is 0, and then, so this is a KKT point. So what is a 0 here? It is also the set 1, and a plus is the empty set. So there is no strictly active constraint at this point. What will be the critical cone? It is, okay, in this case it's again simple because it's the same as the tangent cone, I realize, because it's such a simple problem. So in this case, the critical cone is the set of all x, of all p, so that p is positive. I could compute that, but I mean, this is like at the positive directions. And now I can, because it's a KKT point, I easily see that this is a second, that this is a stationary point. But now, how do I check that this is optimal? And I could now check my second derivative of my Lagrangian only in that direction. And in principle, I only need to check it for positive p. So this is still not a very exciting example, and for the more complicated examples, I would need to do something like this example in 2 dimensions, and I will just illustrate it to you. So imagine now a similar problem, but in 2 dimensions. Now I plot it from the top, and I have x1 and x2. And now I have the problem of minimizing x1 square plus x2 square, so it's an objective function which has its minimum here. And the constraints are subject to x1 bigger than 0 and x2 bigger than 0. So then the critical cone will be only these directions. And interestingly, and this is maybe the thing that I should have made differently with this example, I could add even some other things to my objective. Namely, I could add negative curvature in this direction and still have a minimum. So that would be a complicated case for this theorem, where this theorem, so to say, makes a difference. So how do I do that? So I want to add some term which is not adding anything on the line where x1 and x2 are the same. So if they are the same, I don't want to add anything. So I would have something like minus epsilon times x1 minus x2 squared. So now I got some negative curvature. This negative curvature will be in this direction, and I can still keep positive curvature in all the directions which matter, namely in this direction. It's difficult to check this condition in practice, because we have a conic set, and to check that some matrix is, so to say, positive definite on a conic set is a very hard computational problem. It's not something we can test by eigenvalue decomposition and so on, but it is the condition that is mathematically the right one. You see that everything here gets complicated because we have the weakly active inequalities. So what happens if we have only strictly active inequalities? Let me just add this here. Things get much nicer. How nice do they get? So if we have only strictly active inequalities, then our critical cone gets a simple set again. Because if we don't have weakly active equalities, then the critical cone will not have this thing here. Sorry, the critical cone. It will only have equalities to define it. So the critical cone is an affine set, and I could find a null space basis for this, and then I can again project my Hessian matrix onto this null space, and then I can check eigenvalues. So for if the weakly active constraint set is empty, so if I don't have weakly active constraints, then the critical cone is an affine set. It's a what is it? It's a space, right? Let's just call it an I keep it an affine set. I forgot the name at the moment for an affine set that goes through zero. What is the name for that? It's a. What is it? Sorry? Affine space. Yeah, but it's not affine. It's passing through zero. But anyway, it doesn't matter here. Sorry. Yeah. Sorry. Yeah, actually it is a vector space, you're right. Mm-hmm. We could just say, that is good. Yeah, passing through zero. So I'm complicating things completely here. That means a vector space. But the main point is, and this could be spanned by some matrix Z. And that is the null space basis again, and we could actually compute it, we could project our matrix into the eigenvalue decomposition, and so on. So then we would just check this thing again, and that needs to be positive semi-definite or positive definite, and that's something we could check computationally quite easily. Yeah, so we see that these conditions get slightly complicated when we have weakly inequalities, but that's like it is, and we need to know about this condition. And I wanted to share it with you so that you know that they exist. Yeah? So the second order conditions for inequality constraint optimization, they require positive definiteness of the same Hessian that we always regard, namely the Hessian of the Lagrangian, but on a restricted set of directions, only those directions which are in the critical cone, and the critical cone is less than the tangent cone, and possibly a cone, and in some fortunate cases it is a space, and then it's easier to check these things. Okay, that's the first part, and what I want to continue in 10 minutes is algorithms for inequality optimization, and we will start with quadratic programming, which is like the simplest case, but let's first have a break of 10 minutes. Okay, so now that we have analyzed the optimality conditions for inequality constraint optimization, we can see what we can do with it. And this chapter is about inequality constraint optimization algorithms. And we will restrict our attention to the case of a problem where we have only inequalities. And the reason is that otherwise the notation gets clumsy and the ideas don't get more exciting from always having the equalities around. So I will just start chapter 14 about inequality constrained optimization algorithms. And we will only regard a problem with inequalities. So we have actually f of x, x in Rn, and the only set of constraints are h of x. That should be bigger than 0. Now where h is a function from Rn to Rq, as before. And this is just for simplicity. Yeah? If we would have equalities here, then we would also have equality multipliers. Our Lagrangian would look more complicated, and the algorithms would be nearly the same. So it makes a lot of sense for the teaching that we just drop the equalities here. So what are the KKT conditions? And maybe we should also have the Lagrangian. What is the Lagrangian here and so on, right? So what is the Lagrangian? So L is now depending only on x and mu. There is no lambda. And it's f of x minus h of x transpose times mu. And our KKT conditions are now that the gradient of the Lagrangian with respect to x at the optimal point, mu star, should be equal to 0. And then the remaining terms are the complementarity conditions. h I x star should be positive, mu I star should be positive, and the product of mu I star and h I at x star should be equal to 0 for I from 1 to q. So these are the KKT conditions. And if we have a convex problem and we solve these KKT conditions, we know even this is a global solution. So it's worthwhile to think about algorithms, how to find solutions to the set. And the first class of problems that I want to look at are the QPs. Maybe I should first say one thing. I already mentioned that this set together is a non-smooth set. So linearizing these equations and setting something to 0 doesn't make sense here, because it's a non-smooth set. I cannot linearize. So Newton type optimization cannot be applied without any change. So I need to adapt Newton type optimization in order to deal with this non-smoothness. And there are many different ways to do it. And the first one is easiest explained at quadratic programming. And let's just look at this simple case. It's not so simple. It's actually a pretty complex algorithm, but it's something I want to start with. It's QP solution via what is called an active set method. And so for this chapter, or for this subsection, we will regard a problem where we have our objective being a QP objective, and that means that we have a gradient and we have a Hessian matrix as the objective, and then for our constraints we have ax plus b, and they are positive. So that's the problem we want to look at. And the first thing is to write down the KKT conditions for this problem. And I can write them down. Let me first write them down like that. What I will assume is that it's a convex QP, so it's really sufficient to find a KKT point in order to have a global minimizer of the problem, right? So that would be a nice thing. So we assume this thing, and we can later discuss what happens if it's not the case. So what are the KKT conditions? The Lagrange gradient must be 0, so it's the gradient of the objective minus the gradient of the transposed constraints. So let me just state them. So what are the KKT conditions? They will just say G plus B times X star, that's the derivative of the objective, minus, and then the derivative of this thing is actually A transpose lambda star. There is no derivative with respect to X for this, so this is 0. That's the condition corresponding to this Lagrange gradient condition. Maybe I should first have the Lagrangian, so that we see what the Lagrangian is. It's actually this thing, right? That is the Lagrangian, but if I take the gradient with respect to X, then it's this term which is remaining. So now these other conditions are, of course, Ax plus B, and then the ith component. How do I write that? I can actually still keep it for all components together, so this should be bigger or equal to 0 for all components. Also the mu's should be bigger or equal to 0, but then for the product I need to separate them. Ax star plus B, and here the ith component, that should be equal to 0 for I from 1 to Q. So these are the KKT conditions. It's just writing them down, so there was no really a new thing about this. But what I want to do now is I want to find some points X star and mu star that satisfy these conditions, and we maybe and the question is, how do we find them? Is there? Sorry? Thank you. Very good. So there's a mu and a mu. Is it? Are there more occurrences of a lambda? So there should be no lambda in this whole chapter because I omitted the equalities. Thank you. Was a good syntactical test. So whenever you see a lambda, please shout. Okay, so the question is how to find X star and mu star and an active set. So that KKT holds. And this is the task that we want to look at. And I say and an active set because if we know the active set, then some of these inequalities will be equalities. We know, because that's what an active constraint means, that this thing holds with equality. And if you would know which ones hold with equality, then you could actually have a linear system that we can solve. And that's what we want to end with. And I will actually translate these conditions into a new formulation that is completely equivalent, but which is more computational and which will then lead directly to active set methods. So let me just make some definitions for index sets and index variables, because otherwise our notation gets very clumsy. You see already here I have indices, and from now on I will actually search for an active set. So the idea here is try different guesses for the active set. For A. And these guesses we call A. So actually we define some index sets which are not necessarily the active set, but they are related to the active set. So actually we define this set to be a subset of all the indices 1 to Q, and that will stand for the indices that we think could be active ones. And we define another set which I use with this sig I, which is just the set of all these indices 1 to Q, but without A. So it's the other one. So it's just a division of all inequalities. Yeah? And so then we do a vector division, which is depending on these sets, and which is a bit misusing notation. So when we have, for example, a B, like here, this vector B is of the dimension Q, right? It has all the components of all the inequalities, but we will divide it into two components, one which I call BA and the other I call BI. And I could always achieve that by reordering my vector into the ones that are in some set A, and then by I will always mean the complementary set of this. So A is a guess for the active set. Maybe set guess. That's actually what it is. And this is an inactive. That's why I choose the letters A and I. Okay? So, we have vector divisions, which we will use for our notation from now on. And I will also do a matrix division. So I will also say A, the matrix A, is given by some matrix A, which contains only those rows which correspond to the sets, the components in the set A, and then there's some other rows which are in the remaining. And also for the mu, whenever I have a mu, I will divide it also into a mu that corresponds to the A and a mu that corresponds to the I components. So this is a computational step that is just resorting things. Whenever I change my set A, it will automatically change the set I, and then I will, so to say, have it different when I say BA and BI. They have the meaning of the components which correspond to either the set A or the set I. Okay? This is just a definition. And maybe I should say that, for example, with this notation, I just show what this example, if I write, for example, AX plus B is bigger than 0, that's a statement which is now, which I could equivalently write AA plus BA is bigger than 0, and AI, X plus BI is bigger than 0. So that's just an example. So I can either require them in this form, or I can require it for the one set and then for the other separately. And I want to separate between them, so later on these things, or in the next theorem, they will already be used differently. So what I will now prove is actually I will just use these KKT conditions and write them in a different way. And this lemma is now making a division of the constraints into active and inactive ones. And then some conditions that need to be satisfied, which are actually the KKT conditions, but which are computationally more attractive. Let me state them. So X star is a global minimizer of the QP, if and only if. So that was this necessary and sufficient condition for convex problems that we had. And now I don't say if there exist multipliers, but I say if there exists a definition, if there exist index sets A and I. So I is actually just the complementary set, so I could also just say there's an index set, and a vector mu star A. So I'm only referring to the components of the multipliers in these active constraints. So that the following conditions hold. So that first of all the Lagrange gradient should be 0. So I will have G plus B times X star minus, and now it is interesting, I will only refer to those components which are in this set A. So here I will have mu star A, and here I have an A transpose. And this thing should be 0, because I will implicitly actually set all the other multipliers to 0 anyway, the inactive ones. So this is one condition. I will also require that my active constraints, so these A times X star plus BA, so for this set, I want that they are holding with equality. So these are possible active constraints. So now I have some equalities. Please note that I got rid of some of the inequalities. And then I require the rest. namely the inequalities should, of course, the others, the inactive ones of the they should also be satisfied. And of course, I also want that my multipliers, these mu A star, that they are positive or zero. They could be also zero. And I will actually, I will then just introduce mu star. Sorry? No, they are. This one? Yeah, larger or equal to zero?
Equal as well.
Yeah, I'm just relaxed at the moment. I just maybe let me just state these things. So these are the conditions that I want to. It's a replacement of these conditions and it's equivalent actually, and I will just discuss it in a minute. So I will actually use this definition with mu I star being equal to zero and of the right dimension. So the inactive multipliers I will anyway choose to be zero. And X star is a global minimizer of the QP if they exist index set A, so that these things hold. And the reason is that I could then actually make a Lagrange multiplier where I just extend this with zeros. And because I extended with zeros, I could also add these zeros here, and then this condition is corresponding to the first one. Then I will also have this and this together implies actually that the things are at least positive or zero. So the multipliers are also all positive or zero. So the mu I are positive or zero, and the mu i's are actually exactly zero. And the complementarity I got rid of by this set selection, because by definition, whenever I have mu something in the index set I, the multiplier will already be zero anyway. So these are, it's not necessarily exactly the active set or the weakly or the strongly active set, so I'm not having strict inequalities here. It's just a different statement of the KKT conditions. So this statement is a bit interesting, and the reason is the following. I have some X star here, and I have a mu and a mu star A here. And these two things are equalities, and these two things are inequalities. And the interesting thing is that this system of equations, if I take these two things together, has exactly the right dimensions. It's a square system of equations for X star and mu star. So what I could do is I could test, and this is why these conditions are chosen. I could check, I would choose some arbitrary set A. So this set with a sig A. Yeah? I choose it, then I can see if I can solve this linear system for X star and mu star. It's actually a KKT system, and afterwards I can check if these two conditions are satisfied. And this way, if they are not satisfied, I need to change the guess, and this is the way how an active set strategy actually proceeds. So this the dilemma, I don't prove, but I hope that you agree with me that these are actually, it's just another statement of the KKT conditions. So if there exist multipliers that satisfy this thing, then this product will be zero, and I could just take, for example, the strongly active constraints, for example. It doesn't matter, I can either take the strongly active constraints at A, or I can take all the active constraints as the set A, or anything in between. And then it will satisfy these conditions. And with the set A. And the other way around, if I have such a set A and it satisfies these conditions, then I can extend my multiplier vector with this, and I will actually have found a point that satisfies these conditions. Yeah, so maybe I should just say that the set A is, how do we express that? It's something, yeah, actually, this is the way to express it. So the set A is, of course, it's a subset, or possibly equal to the active set at X star, and it is, it must contain the strictly active constraints. Yeah, so, but anything in between is possible. So there's some freedom here. You can, but if anyway, you can. If this is satisfied, you have an easy way to find a KKT point, and if you have a KKT point, you can choose any A in between, and you will have these things satisfied. So in that sense, the things are really the same. And so what I should note actually is that this is a square system. So if I have these two first conditions, maybe I give them some numbers. 1, 2, 3, and 4. And then 1 and 2 are a square system, linear system. So I could in principle solve it with linear algebra. So what is the system? It is actually G. Here is it's a BA. And then it is plus a B here, and here is an A. Here is an A transpose, here is a 0, and here are the variables X star, and here is a minus mu A star, and that should be equal to 0. So that is equivalent to 1 and 2. And I could, in principle, if I fix my set A, I can directly compute X star and mu A star are a function of A. So I could just fix a set, and then I could solve this linear system if it is if this is an invertible matrix, and then I get some values for X star and mu star, and then I can check these other conditions, and that's what the first algorithm, the algorithm draft, does actually. So let me state what we call algorithm 9. Active set method. Idea, it's actually the basic idea. How will it go? It will actually choose a set A somehow. Just guess it. What could be the active constraints? Then you solve for only these two equations. Solve 1 and 2 to get X star and mu A star. So you get these things. Actually, you can, by this definition here, by just extending it with zeros, you can also get the whole mu star. That's trivial. But then what you do is you check that the other two conditions are satisfied. These are the two non-trivial conditions. It could be that by this linear system violates now the other constraints, which are not part in that, or it could be that the multipliers, some of them get the wrong sign. So both of these things can happen. Check 3 and 4. There are two cases. If they are satisfied, then you have a solution, right? And else, change the set. And how we change it is, of course, something that depends. Else, change A by adding or removing constraints. That's it. And then you usually add only one at a time. One more, or you take one away. And that is how an active set strategy proceeds. And now we need to find out how that can be done. And I want to point out only one possibility, and that is called a primal active set method. But I maybe mentioned before that many variants exist. Variants for updating A exist. And so there's one thing that's called primal active set strategy. There's also something that's called a dual active set strategy. Active set strategy, 3 dots. There's also a primal dual. Active set strategies, and there are some things that are called parametric active set strategies. So there are many possibilities, and different QP solvers have different of these strategies implemented. I will now only discuss the primal active set strategy so that we get an idea of how that works, and it's relatively intuitive and easy, I would say. But let me discuss it. And I think it's maybe better that I don't even write down the algorithm, which is a long algorithm, but I will just explain it in words, and then we go through an example to do this, apply this algorithm to this example. Okay. So what the algorithm does, it's algorithm 10, and I will sketch it at least in some form, primal active set strategy. And the first thing is it chooses a feasible starting point. That's a very important point. Choose feasible x0 with active set A0. We call it A0. Yeah? And then we have an iteration index k that starts at 0, and then we go on. And now we will really do what we do here, namely we solve for this given active set this optimality system, and then we have a new point which is optimal if we would assume that this set alpha k is not alpha, ak is the active set. And yeah, I think I will illustrate it on a line first. So what we will, it could be then that this point that we get, the solution of this thing, that the x is a feasible point again. If that's the case, then we could just move there and we get a better feasible point, right? But it could also be that we are getting infeasible, and then we could just move as much as we can before we get from the point where we are, x0, we could move to the solution point of that system until we meet a constraint which is getting infeasible. And then we just add this first constraint where we get infeasible to the active set, and then we have a new constraint. So I think I will explain that directly at one example, okay? So this example is, so you actually add constraints by trying to optimize a point, and if you cannot improve your point anymore by adding constraints, you will actually check that your multipliers have all the right sign, and if some of them have the wrong sign, then you drop the constraints which have the wrong sign, namely the negative one, then you drop one of these constraints, and then you make your active set smaller. I think I want to illustrate it with an example before I write down an algorithm. instead of writing down the algorithm. The algorithm is in the script, so it's nasty. But I want to just look at this example, minimizing x squared. So it's a two-dimensional example, again, x in R2. And my constraints are, actually I have three constraints. x1 is bigger than 1, and x2 plus 1 is bigger than 0. So here I could also just say x1 minus 1 is bigger than 0, right? And then 1 minus x2 is bigger than 0. And how does this example look like? It looks like this. I have a feasible set where I have this constraint x1. So I have my variable, here's the point, here's x1 and here's x2. And I say that x1 should be bigger than 1, so that is this constraint here. Then I say that x2 should be bigger than minus 1, so that is this constraint here. So this is the first constraint, this is the second constraint. And then I say that x2 should be smaller than 1, and that is the third constraint. Okay? So now I start with some point, and let me just be consistent. We choose, for example, and then we have the example that I have in the script. I could choose this point. x0 is this point, and I choose also the active set that corresponds to this point. And so I start with a set A0, which is just given by 3. Okay? So now I have a starting point that is feasible, and I have a feasible and I have a set at this point, an active set. And what I now do is I solve the system that is optimizing the problem as if there would be no inequalities, and as if this one constraint would be an equality constraint. And we know how to solve that. We will just solve actually on this line the optimization problem, and the objective function in this case is just here. So the minimal point will be here, that point. So this will be the point which is the solution of our linear system. And what this strategy now does, the primary active set strategy, it first checks if this point is a feasible point. We see it doesn't. It violates this one constraint. So what you can then do is you can move from x0, and I should give a nice name. This point here I call x0 tilde. So it's the optimizer that satisfies the optimality conditions. So here we find actually x tilde k and mu tilde a k by 1 and 2. So you actually solve this linear system of equations, and then you go on a line from xk to x tilde k. So you go on a line until you leave the feasible set, because you are on a feasible point, and because the feasible set is a convex set. On a line there will be one first point where this will not be feasible anymore, and afterwards all points are infeasible. So then you stop at this point. And because there was a reason this constraint cannot be violated, because it's always kept at 0 in your solution. But there's one constraint added here, and then you add this extra constraint. So in the next iteration you will actually have this point that I call x1. So this is the point where you stop. It's done. It can be computed quite quickly if you know x0 and x0 tilde. And here you now define a set A1, which is the original set, but you add another index, and namely you add the index 1. So now what you will do is you will compute the solution for this constraint and that constraint fixed. You have two variables, two active constraints. So that will actually solve an optimization problem which finds this point as a solution. And that is the optimal solution if that constraint and that constraint should both be active. But it's not an optimal solution to the original inequality constraint problem. And what will appear here is actually that this multiplier for this constraint will have the right sign. This is something we would need from computing. But the multiplier for the other constraint, for this constraint number 3, it will have the wrong sign. So afterwards you will check actually the multiplier, and you see that here, after you solve that, you get x1 tilde, which is the same as x1. Yeah? So that's the same thing. But you get that the mu tilde of which constraint? The third constraint is smaller than 0. And at this moment you will actually drop it. So now you will decide to drop your wrong constraint, and you will actually now choose alpha, the set A2, which has this bad multiplier is dropped. So the constraint which has the wrong sign you drop, and you will choose as x2 just the point that you had x1, namely. So now I'm at this point, but I have only this constraint as an active set guess. And now I can solve the problem of minimizing my objective along this line, and I will find this point here in this case. And at this point I will have, so this is actually x2 tilde, right? So it's the solution of the problem at x2. And I can go the full way to the end here. And at this point I will now be feasible, I see. I could do the full way, so it is a feasible point. But I can also check the multipliers, and there I will see there is only one multiplier corresponding to this constraint, and it will have the right sign, and then this is the solution to the algorithm. So what the primal active set, I didn't write down the algorithm, I didn't explain it really, but I explained it as a procedure. So what you do is you start feasible, you start with a guess, you solve equality constraint problems. If you go from this feasible point to the new solution, you might be blocked by some extra constraints. When you are getting blocked by constraints, we add them to the active set guess. That way we add more and more constraints to our problem. Once we have added so many constraints that we don't move anymore, we look at the signs of the multipliers of these constraints, and then we drop those which have a negative sign. And that allows us then, because we remove some constraints again, then we start to move again. And we will move then in some descent directions. And this is the little thing that we didn't have, or that we would need to know here, is that when we remove a constraint, we will, with a negative multiplier, that then we will improve our objective. So actually what this strategy does, it goes at some active set guesses, it goes always down. It will actually improve the objective. That is what is called a primal active set strategy. But as I said, there are other active set strategies as well, but this is one which is very often used. Most important is that you know the rough idea, namely that you basically solve equality constraint problems, and then you check that the equalities, these two extra conditions, are satisfied. And if they are not satisfied, you have to modify the set, and in a primal active set strategy you decide first to add all the things that you can add, and once you cannot add anything anymore, then you start to drop the things which are related to these. And sometimes some other strategies first work on the multipliers, and that's the dual active set strategy. So this is the rough idea of active set strategies in a nutshell. And I think that's it for today. And I want to continue with other topics next time. So I thank you very much and wish you a nice afternoon.